My name is Ilkan. I'm from CISPA, and I'm presenting our accountable JavaScript code delivery paper. This is a joint work with Pascal Berrang. He's an assistant professor at University of Birmingham, and he works at Nimiq. And Katriel Cohn-Gordon from Meta, and Robert Künnemann from CISPA is my supervisor. So the web is ephemeral. A user that accesses a web application today has no reason to trust that it will be the same application yesterday or the same application that other users receive. The web page might look like the same, but the active content, such as JavaScript, could have changed in some other access, and there is no mechanism in the browser to tell this change. A compromised or malicious web server can easily target classes of users by sending different code to different users. For example, the web server might insert malware based on browser fingerprint, or the web server might use the browser for cryptojacking, and many more issues can happen. Hence, there is a lack of trust between developers and users in the web environment. However, for some websites, establishing and maintaining the trust between developers and the users is part of the business model. For example, ProtonMail wants their users to trust that they really encrypt their emails. Nimiq, which we use in our case studies, they provide a web-based payment platform using Nimiq's cryptocurrency, and they want users to trust that they don't have access to users' funds. And WhatsApp, one of the most used messengers, they recently published a browser extension that allows users to trust that the web client keeps their messages always secret. The extension is called Code Verify. I will come back to it later. There are common risk mitigation strategies comes to one's mind to achieve these goals. One is auditing. Auditing, a developer that wishes to build trust among users can employ external audits to inspect the client-side code. Auditing works well where it is possible for the user to verify that the code they are running is the same code that was audited before, such as when the code is distributed by an app store. However, it doesn't work for web applications because a malicious web server can simply decide to deliver unaudited code to the user at runtime. Second risk mitigation strategy is accountability, where the developer can be held accountable for the code they deliver. Again, this works for app stores, where the code is reviewed and the developer's identity can be linked to the malicious code easily. However, it doesn't work for web applications again because there is no public record of the developer's identity or the malicious code. So there is no way to hold the developers accountable. In this work, we provide an opt-in accountable JS protocol. We provide accountable delivery of active content using efficient and easy-to-use code signing technique that brings authentication of origin. We use public transparency logs that brings the proof that everyone receives the same code in a time frame. And we reinforce the HTTP request response procedure with a non-repudiation subprotocol that brings the proof that that content was received by an individual user. We also prove these properties with automated protocol verification tools, Tamarin, and stateful applied calculus APIC. At a high level, we propose a web application developer who chooses to opt in provides a signed manifest enumerating all of the active content in their web application. We also develop a browser extension that measures the delivered active content and compares with the manifest metadata in the manifest. The manifest files are stored in publicly readable transparency logs in our protocol. We see the web server as a software distribution mechanism, so we separate the developer and web server. In the protocol, developer signs the manifest file and sends it to the log. Then the log signs again and sends it back to the developer. Then the developer puts this signed manifest to the web server for end users. A manifest file looks like this. It's a simple text file in JSON format, and it enumerates all of the active content in the web application. It provides the URL, manifest version, and some optional information about the web page in the manifest header, and it lists metadata for each active content in the manifest body under content section. Typically, an active content metadata includes a sequence number, type, and trust values. Sequence number shows the order of the active content. Type can be inline or external JavaScript, or event handler or an iframe. And each active content metadata must have a trust declaration value. The compliance check method is decided on this trust value. Trust value can be assert. The developer, in this case, provides hash of the active content. Therefore, she asserts that the code behaves as intended. In the compliance check, we compare the delivered hash against the hash declared in the manifest. We show the trust values on some case studies. A possible case study for this assert value is self-contained application such as WhatsApp Web. In WhatsApp Web, the code is bundled and served to all users, and personalization is implemented through local storage and dynamic data fetching. In this case, the developer can vouch for their own content and declare all of the elements with the assert value. Second case study is trusted third-party code. For example, the web applications that rely on common JavaScript libraries such as jQuery. In this case, the developer pins the third-party code to a precise version that is trusted or inspected in advance. In this case, again, the code that comes from third-party, as it is trusted, it can be declared with assert value. The second trust value is delegate. In this case, the developer refers the trust to the third party that provides the element. Now the third party is taking the responsibility for this code, and the browser requires a separate manifest for this element. A developer that doesn't want to vouch for the third-party content, or if she always wants to use the latest version, can use this delegate option. A possible case study for this is Nimiq Wallet. Nimiq Wallet provides a web-based payment platform using Nimiq's cryptocurrency. The Nimiq Wallet can be embedded by first-party applications that provides a web shop, but only if the Nimiq Wallet makes itself accountable for the code it delivers. The third and the last option is blind trust. The developer blindly trusts the active content without identifying the code. This is used when the code cannot be audited and the code doesn't use accountable.js, such as the code that comes from @bidding. In this case, the code that comes from @bidding can be declared with blind trust in the manifest, and the developer is responsible to properly sandbox that code. In the compliance check, we only check this sandbox values in the HTML and the manifest file. A possible case study for this is the untrusted code that comes from AdSense. In this case, the code that comes from @bidding can be declared with blind trust, and it can be sandboxed. And we also combine the secure code in this case study. We add the Nimiq Wallet as the secure code and declare it with the delegate. However, the sandboxing the AdSense code doesn't work, because the AdSense requires the active content inside the AdSense requires access to the top level window to detect invalid clicks. So we flip the relation in this case. We sandbox the secure code instead and leave the AdSense code as is and blind trust it in the manifest. The content that is delivered to the browser should be measured in the client side and compared with the manifest file to find out if it adheres to the protocol. The image shows the measurement procedure in which we inject content scripts to the top level window and nested iframes. The content scripts observe the DOM using the mutation observer and collect metadata for each active content in their domain. And the content scripts inside the iframes are also responsible to send their collected metadata to the top level window using post messages. So the top level window collects all of the metadata and sends it to the compliance checker. The compliance checker downloads the site manifest, verifies its signature, and compares the active content metadata with the manifest to understand if it adheres to the protocol. The same procedure can be used to generate a manifest file for a website in the development mode. We applied compatibility and performance analysis on the case studies. We evaluated our accountable.js extension to find out how much it affects the page load time using standard metrics of Lighthouse. I only show 2 of them here, but there are others presented in the paper. This table shows our evaluation results. The table on the top, the subtable on the top shows the evaluation Lighthouse metric results for the case studies. The values on the left are baseline values. They are computed when all the browser extensions are disabled. And the second value on the right shows how much it changes when accountable.js browser extension is enabled. We consider the changes below 100 milliseconds as imperceptible. As can be seen in the table, all of the values are imperceptible. The subtable at the bottom shows the WhatsApp Web evaluation results. WhatsApp Web is incompatible with Lighthouse, so we used Puppeteer's page metrics results in this case. So again, the baseline value is when all the browser extensions are disabled. Second value is only the code verify is enabled. And third value is when only the accountable.js is enabled. We should remark that accountable.js's browser extensions total page load time is very good with respect to the code verify, because the code verify doesn't support most of the operations that accountable.js provides. I feel like many web security people are asking the same question: why not just use the content security policy? Content security policy lists the valid resources in the web page, and this allows executing the unknown resources in the browser. But it doesn't solve the accountability problem, because a malicious web server can simply decide to deliver a different content security policy or not deliver it at all. Also, content security policy is not designed to know the order of resources in the web page. This can be used as a mechanism for micro-targeting. Resource A loaded before B might mean something different from B than A. This is covered in accountable.js. Furthermore, content security policy doesn't support delegation. In accountable.js, we allow the third-party content to vouch for their own content, and the developer of the main website doesn't need to update its own manifest each time the delegated manifest is updated. This is very convenient for developers. The second related work is code verify, as I mentioned before. We were in close contact with Meta's WhatsApp team in the beginning of this project, so this might be or might not be related to accountable.js. They likewise implement accountability for active content, but only for Meta websites for now. In the protocol, WhatsApp developers submit a hash on their JavaScript along with a version number to Cloudflare. Then the Cloudflare publishes this information for the end users. Then when the end users accesses to the WhatsApp servers, they download the JavaScript files, and the code verify computes a hash on the downloaded JavaScripts and compares with the hash that is provided by the Cloudflare. Given that the manifest is hash not signed, the Cloudflare is trusted for authenticity, and it replaces the transparency logs in accountable.js. Also, Cloudflare doesn't give any information about the history of submitted versions or which one is the most recent, as the public cannot inspect how often the versions have changed. It relies on Cloudflare to implement countermeasures against micro-targeting. In conclusion, with accountable.js, developers being held accountable for the code they deliver creates confidence in operations that the security critical websites provide. It also enhances the security by creating a deterrence mechanism for behaving dishonest in the web, and it increases transparency as the public can inspect how their data is being used by whom and so on. In the future, we hope to become part of the browser and become a standard someday. In addition, you can find more information about these topics in the paper. Thank you very much for your attention.
Hi, I'm Nimiq from West University. So the simulator you made JavaScript code accountable. But a lot of like honored JavaScript applications seem to rely heavily on like RGC calls and transport JSON data, and it seems like that data could impact the control flow or the JavaScript code a lot. So even if you keep your code accountable, if the data that's being queried from servers maliciously changed, they get a malicious like developer may be able to cheat the behavior of their code just by changing like JSON data. How to avoid ways to protect against this type of attack with like modern like JavaScript applications that like developers are probably so huge that it would be difficult to protect against this type of thing.
You mean the changes after downloading the code and the developer creates the like the browser, or do you mean the non-active or that attacks?
Yeah, so like the JavaScript code does a XML and HTTP request, gets some data, and either parses it or deserializes it. It uses that as to inform like what it should do further in its code. And if the developer maliciously changes the data, sometimes it seems like you're not fully the data schema or accountable.
Yeah, but this one is still can be audited by what's searched in the law, and this makes them accountable for what they deliver in the end, right? So we don't know anything about this quality part, but we are waiting it is easier to what first to inspect the client's thing.
Okay, thank you.
Other questions?
Thanks for the talk, and I think I really asked about sharing of trust here. So isn't that there needs to be somebody to sign here, and who's that party and why and how we can trust them? Particularly if it's the developer themselves, then how does this keep right from this ethic in hashtag, so ending a hash attribute in the script tag? And if it's a third party, then is it possible for the third party to sign some malicious code act?
It's not possible to sign the code. What code should be signed by or for a different certificate. The certificate. I'm not sure really understand the question about the first part, and we can make it more signing. I mean, I'm sure about it. Outward and so.
We have time for one more question. Costas, if you want to start moving up further the station, we can. Over budget. So I have a quick one. I understand during your delegation aspect of the trust. But leaving that aside, like if I could, as a website developer, know all the hashes, it would also roll out significantly better the CSPs. Because I don't think the CSP sources you do. I'm just saying that with the studies that we've seen so far without CSP, code seems to be changing so rapidly that developers simply can't keep up with choosing the correct hash to all the active content that they have to benefit their application. So why is this not an issue or what we're talking?
Well, what? And should discover then what's the situation that they and that's a bit much.
So your scheme presumes that the Java web application knows the hashes for all the active content on the content that they produce will load a third party.
Right.
Many of studies for CSP action, this is notoriously difficult and is not implemented by the vast majority of it. So why is it not an issue for when it's illegal? Yeah, don't worry about it. Happy to talk about it offline because I'm really that's it. Sorry about it.
It's just I'm excited.